Okay, this is part 2 of what will be 3 parts of the redox or oxidation reduction reaction lecture. Last lecture I just went over what redox is, how you identify it, and how you apply or calculate oxidation numbers. So this lecture I'm going to work through a number of problems and show you how to write the redox reactions. Okay, let's just go to the slides real quick. So I showed you these rules, and then I showed you Tyler DeWitt's, which I think are just much more concise and easier to understand. Just to remind you, your 2 simplest rules are your element is pure element is 0, and your simple ion, your monatomic ion, is the ion charge when you have a single ion. And then the sum of all of the oxidation numbers have got to equal the sum of the ion charge if it's an ion, or 0 if it's a molecule, because of course that's not charged. And then after that, we start following the rules in a particular order. Fluorine is always number 1. Hydrogen is either +1, -1, depending on if it's with a metal or a non-metal. 1A is +1, 2A is +2, and those are some of the most common ions you're going to see, or so that makes it helpful. 7A, your halogens, usually -1, but not always. This is where we go back to rule 3 and we calculate them based on what we do know, which is usually going to be 1A, a 2A, or an oxygen, which is most of the time is -2 unless it's in peroxide, which you are very rarely going to get peroxide. But if you do, it's a -1. So there are a number of examples in the slides, so I'm just going to work through them so you can get comfortable with work through them. And then I encourage you to go back on your own and work through each of these so you just get comfortable assigning the numbers. Remember, it's all bookkeeping. And the other thing to remember is that the oxidation number is on each individual atom or ion. It's not on a molecule. It's on the individual, and it's on the individual single. If you have 2 oxygens, the oxidation number on the top will be for each oxygen, not the sum of them. Okay, let's go to the whiteboard. So the first example, and these start simple and they just get a little more complex, is lithium oxide. Okay, remember this is an ionic compound. Lithium is a metal, oxygen is a non-metal, and so you have, this is a formula unit or an ionic compound. So let's look at Tyler DeWitt's rules. In fact, let me rewrite my ionic compound up above a little bit. So we don't have an element by itself. What we do have, though, lithium is a group 1A. It's right here. So we have that rule. And a group 1 is always +1. So the oxidation number is going to be +1. And you write it on the top and you write the sign first. And then oxygen here is usually -2. It is not a peroxide, so it is in fact -2. And let's just double check the sums, because the sums have got to equal 0, because this is a neutral compound. So we have 2 lithiums. I always do my work underneath my molecule or my compound. So I have 2 times a +1 going to do it in color. Just do it in black. So you have 2 lithiums times a +1 is going to give you a +2, and you have a -2. So in fact, you do have 0. So that's a very simple example. Your math that goes down at the bottom is where you sum your oxidation numbers with how many of each atom or ion you have. The oxidation number is on the top, and it's for each individual, in this case, ion. So the lithium is +1 and the oxygen is -2. All right, the next example is CO2. This is covalent. We apply oxidation numbers to both covalent and ionic molecules. All right, well, oxygen, every time you see oxygen, you should be happy, because unless it's a peroxide, it's -2. Carbon is one of those you are going to have to figure out. So I have 2 oxygens times a -2, right? So that gives me a -4. Therefore, because this is a neutral molecule, my charge on the carbon has got to balance that. My total charge is +4. I only have 1. So therefore, the oxidation state or oxidation number on that carbon is +4. All right. And again, you write it on the top for each individual element or atom. Okay, I'm going to erase these. And we're going to go to the next slide. It starts getting a little more, not too challenging, but a little more twist. This time we have perchlorate ion. We have a charge. And so what we sum is going to equal -1. It is not going to equal 0, because the rule is the sum of the oxidation numbers for a polyatomic ion is equal to the ion charge. So once again, oxygen, this is not a peroxide, so oxygen is -2. I have 4 of them. So 4 times -2 is -8. So my chlorine has got to balance out the oxygen such that I have a -1 left over, which my chlorine has got to be a +7, right? So +7 and -8 is going to give you a -1. Now, what if I wanted to work this out with just assigning the rules? So this actually is, right? But what if I went back to my rules and I said, now, wait a minute. I have a rule here. This is oxygen is usually -2. And I have a rule here that my halogens, because chlorine is right here. It's a halogen. It's a 7A, is usually -1. What if I wanted to apply that rule? What would happen? So I want to say, well, that oxidation number is a -1 according to our rules. And this oxidation is, and you can already see what's going to happen. So -2 times 4 is -8, and I have one of these -1. I have a -9. That does not equal the -1. So you have the always rules, the sometimes rules, and the, well, you're going to have to calculate it rules. Most of the time oxygen is -2, and so that's the one we would start with. We would do the math such that we come up with a negative charge, and that was the oxidation number for chlorine of a +7. So you can see that they can have a wide range of oxidation numbers. This actually means that the electron density is shifted completely away from chlorine to the oxygen. All right. So the next one, this is magnesium dichromate. Okay, we have an oxygen. It is not in peroxide, and so we are going to give that the -2 charge. Magnesium is right here in group 2. And the 2A is always +2. So that's going to make that easy. So we have assigned our magnesium and our oxygen. But we have no idea, we do not have a rule for chromium. And so you're going to have to do the calculation. It's going to equal 0 because this is a neutral ionic compound. There is no charge on it. So we have -2 times 7. So that's going to give me -14 and a +2 because I only have one of these. So my sum of my chromiums has got to equal +12, right? Because +12 added to +12 is +14 minus 14 gives me 0. But I have 2 of them. So each individual chromium, you divide that by 2 is +6. And then if you want to double check, we say -2 times 7 is 14, -14. +6 times 2 is +12, and this is +2. So +2 plus 12 is +14, -14 gives me 0. So make sure when you get your sum for your calculated atom or ion, you divide it, if necessary, by that subscript to get the individual. Every chromium atom has a +6 oxidation number. Okay, the next one is potassium permanganate. And these are the slides. I'm just going through them, so you can use these as practice. So oxygen, right? It's not a peroxide. Peroxide is H2O2, most hydrogen peroxide, the most common one you're going to get. So that's a -2. Potassium, where's potassium? Potassium is right here. Potassium is in the 1A. And according to our rules, group 1A is always +1. Let's make that +1. We do not know what manganese is. We don't have a rule for manganese except for the fact that the sum of these has got to equal 0 because this has no charge. We're looking at the whole molecular ionic compound. In this case, it has a net 0 charge. So we're going to calculate -2 times 4. So this gives me a -8. And I have a +1 here. I have to have a charge for manganese such that my net is 0. So this is going to be a +7. +7, I only have one of them. +7 and +1 is +8. -8 is 0. So therefore, my manganese oxidation state is +7. Again, it goes over the top. Your oxidation numbers go on the top of the individual atom or ion. Your math goes underneath, unless you want to do it way above, like in the video. Looking for... looking for one with nitrogen. Nitrogen actually can have a really broad, it can have everything from a +5 to a -3. And basically what's happening, the +5 is from losing the 5 electrons, the -3 is from gaining. So that's the range that nitrogen can have, anywhere from a +5 to a -3. But I don't see any. So if you see nitrogen, make sure that you have to calculate that one. Right, let's go back to the slides a minute. Maybe one will come up. So here are the exercises I just went through. I don't know why that looks like that. So when you write a redox reaction, when you talk about what is getting oxidized and what is getting reduced, when you have that question that you have to answer, whether it's a lab exercise, a homework problem, or an exam question, you are not looking at the entire molecule. You're only looking at the individual atom or ion that actually changes. And I'm going to write this over. We're just going to go ahead and work them out because I just think it's helpful. To have it written as I talk about it. So this was, you have zinc solid plus copper chloride, copper 1 chloride, aqueous. So that's a solution. And that's actually dissolved because the chlorine is actually dissolved copper ions and chloride ions. And when you mix them together, when you put the copper chloride solution in with a piece of zinc metal, you get a reaction and you get zinc chloride, aqueous. So now you have zinc ions in solution and copper metal. So the copper is going to start plating onto the zinc. So according to, let's do the easy numbers first. According to our rules, any single element is 0. So zinc solid and copper solid, they are not ions, they are just elements, is 0. So zinc, okay, and you would look at this and say, well, how do I know? I have a kind of sort of rule for chlorine. I don't have a rule for copper. I don't have a rule for zinc. What you do when you're determining the charges on your ionic compounds is you mentally separate them because this is dissolved. This is a solution. Everything is dissolved. So you mentally separate it into this constituents ions. You write an ionic equation in a sense, right? So this is actually, so it's our 2, so it's a 2 plus. I said copper 1, didn't I? That was wrong. And 2 chloride ions. That's what this actually is because it is dissolved. And here you have the same thing. And these are aqueous. And you know it's dissolved because it's a solution. It says aqueous. Now you can actually look at this and tell what my ionic or my oxidation number is. So my copper is a 2 plus, even though it's not standing alone in this reaction equation. If you wrote it as an ionic, this is what's actually happening, and it is in fact plus 2. And my chlorides are each minus 1. My zinc here is plus 2. My chlorides are minus 1. You can double check this because your numbers have to be balanced on each side. I have a 0. I have a plus 2. And I have 2 times minus 1. So, which is a minus 2 and a plus 2. So that's 0. And here I have a plus 2. And I'm going to have 2 times minus 1. Which is minus 2, so plus 2 minus 2 is 0. So yes, I have a net 0 on both sides. Okay, that's just if you want to double check. So let's look now at who's getting oxidized and who's getting reversed. Remember, I use the Leo. So if you lose electrons, it's oxidized, and if you gain electrons, it's reduced. Okay, that's an L. If I lose electrons, I'm becoming more positive. I'm losing my negative charge and becoming more positive. So my zinc goes from a 0 to a plus 2. It's becoming more positive, and therefore my zinc is getting oxidized. And remember, the ending is important. So you say it's oxidized or it's oxidation. So that's getting oxidized, which means something over here has to be getting reduced. The chloride stays as a minus 1. So that's actually not part of the reaction equation. The copper goes from a +2 to a 0. It's become more negative. You added negative to it, and it's getting reduced. It's gaining electrons. Okay. If you are asked the question, what's getting reduced in this reaction equation, you do not say copper chloride, you say copper ion. Here, that is your answer. The chloride is not getting reduced. It's a spectator. And this is why you often see these written without the spectator ions. Previously, I showed you, and it was written as the copper ion and as the zinc ions. And that's why. It's the actual active parts of the equation. So if this is getting oxidized, that means it's the agent that's allowing this to be reduced. And so therefore, this is the reducing agent. And if this is being reduced, it's enabling zinc to be oxidized. So it is the oxidizing agent or oxidizer. Oxidizing agent. So it's either oxidizing agent or oxidizer. Now here's something I didn't really go into in the previous lecture. Just like you have the conjugates in acid base, you also have the conjugates in redox. Now, some people don't like the term conjugate because in an acid base, you have an exact single conjugate for every single acid or base. You know, HCl aqueous as an acid has a conjugate base of Cl minus. Always, always, always. That's not always the case in a redox, but we'll use the term conjugate, but we're using it loosely. So if you watch a video, you see it called something else, that's why. It's not as fast and firm, but it's still the pair, and the pair is the opposite activity. So if zinc is a reducing agent, then the oxidized form of zinc is the conjugate, and I'll put conjugate in quotation marks, oxidizing agent. And if my copper ion is reduced, the reduced form of my oxidizing agent is the conjugate reducing agent. All you have to do is figure out one of these. Everything else falls into place. And this is why I often will write, when I write my Leo and my GER, I will write reducing agent or reducer. I'll usually write reducing agent. And oxidizing agent, because it's just really easy to get them confused. So I'll actually write that down and I will look back and refer to it so that I don't get them all jumbled up. And I highly recommend it. Okay, all you have to do is figure out one thing. If I figure out my zinc is getting oxidized because it loses electrons, well then the other reactant has to be being reduced. And if it's reduced, it's the oxidizing agent, which means the other one's the reducing agent. If that's the reducing agent, its partner over here is the conjugate oxidizing agent. So you figure out one and then fill everything else out. I highly recommend you write it down on the equation. Don't try to sit there and figure it out in your head because it will, I promise you, all mix together. But if you write it down on your equation, you don't have to get it confused. You just look and you read it off. When you know this is the reducing agent, then you automatically know this is the conjugate oxidizing agent. And it's just the zinc ion. It's not the chloride. Chloride's a spectator. Okay. So this is how one way we write it, or often, like I said, you will see it with just the ions. It depends on if it's a molecular equation or if it's just a stripped down redox equation. Okay, I'm going to go back to the slide a minute and then we'll come back to the board. Okay, so this is what I just went through. And this is talking about your conjugate, quotation mark conjugate, if the zinc is the oxidized, it's oxidized and it's the reducing agent. It's reduced and it is the oxidizing agent. So if you have this experiment and you have a piece of iron metal, so it's Fe solid, and it's placed in a solution of copper 2 nitrate. There's your formula. You get a reaction where the copper will actually become the copper element and build up on your iron. And the iron goes into the solution as an ion. This is blue because copper ion is blue, and this is clear because the copper, in this case, over time, significantly, if not 100%, converted to the copper metal. So we're going to write this. We're going to go through the entire process because this is the lab that you would normally be doing. And so we're going to pretend we're doing it. So we're going to write the equation. You're going to identify each of the agents, what happens to them, and what their oxidation numbers are. Because this is something you'll need to know how to do. So first we have to describe the process, and it says, I'll read it. As shown in the figure, when iron metal is placed in a solution of copper 2 nitrate, a single displacement reaction occurs. You don't have to worry about that. In which copper deposits on the surface of the iron and aqueous iron 3 nitrate forms. So what do we have? We have iron metal. So that's iron solid. Is placed in a solution of copper 2 nitrate. So it's a solution, so we know it is dissolved. The word solution is which means this is actually copper ions and nitrate ions. And a reaction occurs in which the copper deposits on the surface of the iron. That means the copper is becoming solid. An aqueous iron 3 nitrate forms. So iron 3, which means it has a +3 charge, which means you're going to have 3 of the nitrates aqueous. Now it has to be balanced. This is not balanced. I have 1 iron here, but I have 2 nitrates and I have 3 nitrates. So I'm going to make 6 nitrates. And that gave me 2 iron. So I have to put 2 iron over here. And this gave me 3 copper. So I have 3 copper here. And I have to tell you, I am looking at the slide. So normally I would double check this and make sure my inventory is correct. But since I'm looking at the slide, I'm just going to make sure I wrote it down correctly from the slide. But yes, that is correct. Normally I would go through and I would double check my inventory. So there is my redox reaction equation. I have got phases for each one. The first question you're going to get, did a redox reaction happen? Well, what are my oxidation numbers? Iron solid is 0, copper solid is 0. Do the easiest ones first. Copper nitrate is aqueous. That's a solution. That means everything is dissolved. That means you have, and you were told it was copper 2 nitrate, so you know it's a 2+ copper ion. And then you have the nitrate ions. I'm just showing you this is what's actually in there. I'm not bringing the stoichiometry down. And then you were told that a solution of, or aqueous iron 3 nitrate, so this is iron 3 plus, and your nitrate ion. So this is what's actually in that aqueous. And you can use that to determine your oxidation number. So this is a +2. This is a -1. You can do it right now over the whole nitrate because the nitrate's not going to change. You just trust me on that. Because what we're really looking at, I know it's a spectator ion. What we're really looking at is what does change. The iron goes from a 0 to a +3. It is losing electrons. Therefore, it is oxidized. Therefore, I know that the copper has to be reduced. And it is gaining electrons, going from +2 to a 0, so it gains 2 electrons. +2 and -2 is 0. The nitrate is a -1 on both sides. It's a spectator, pretty much always is going to be a spectator. I can't think of a time when a nitrate is going to, it's not going to be nitrate anymore if it's involved in a redox reaction. It won't be nitrate. So if you see a polyatomic just pick up and move, it's not going to change. It's a spectator. So if this is oxidized, then it is the reducing agent. It just is. But I also wrote it up here. And if this is reduced, it is the oxidizing agent. If this is reducing agent, then this has to be the conjugate, opposite of that. Oxidizing agent. And if this is the oxidizing agent, this has to be the conjugate or paired reducing agent. So all you need to learn is one. Once you've identified the oxidation numbers and you know which two, there will generally will be two, at least from what we give you, there will be two, one getting oxidized, one getting reduced. You write that, you can write everything else down. And then when you have to answer further questions, you go back and you look at what you wrote down. The spectator ion is the nitrate. It is not involved. So if you're asked what is being oxidized, of course, you say the iron. You say this, the iron solid. The iron element is being oxidized. You don't say the iron ion. This reaction goes in one direction. Nothing is happening to the iron ion. Okay, it's a one direction. So this is being oxidized. The copper ion is being reduced, not the copper solid. So these are the guys you talk about, what's being oxidized and reduced. You do not include the spectator ion. Okay. So that's how you write a redox reaction. Like I said, sometimes you will write it without the spectator ion, which makes more sense, but this is a molecular equation. This is the pretty one. We include everything. But if you write it without the spectator ion, you just move your aqueous over to your dissolved ion. Okay, I'm going to show you the next 3 slides and then we'll work through them. So here's just work through. And this is a half reaction you will get into in Chem 1. I had someone ask me about this already because they thought this had something to do with balancing reactions. Only for redox. This is not part of your normal balancing reactions like we do with stoichiometry. This is specific to redox. It talks about the transfer of electrons. And when you have it balanced, how many total were transferred left and right? Because when we have this balance, we actually have 6 electrons were transferred left and right. But you will learn that in Chem 1. This is just showing you the process that's happening. Copper gained 2 electrons to become copper solid, copper ion. Iron solid lost 3 electrons to become an ion. So in a half reaction, we actually split them out and we put the electrons in there to show the balance, but that's something you're going to learn in Chem 1. So if you see this, you just say, oh, that's nice, and move on. All right. So we're going to look at these 4 reactions and decide if they are redox or not. And if they are, what are the oxidizing agents and the reducing agents, which means you have to determine the oxidizing agent is the one being reduced, the reducing agent is the one being oxidized. All right, so I'll read each one out as I put it on the board. And you notice I'm keeping this up here because I have to use that or I will get it all scrambled. So the first one is this. Is this a redox or not? So it's 2H2O goes to 2H. So we have some electrolysis going on here. What's not written in here is that we actually put some energy up there. So I'll put that there, but you don't have to. This is splitting water into hydrogen and oxygen gas. So the first thing you do is you look at your oxidation numbers. Well, this part's easy. I have an element here, so that's 0, and I have an element that's 0. It doesn't matter how many hydrogens I have. That's the only thing I have there. There's no charge. It's not an ion, so it's 0. But let's look at water. Oxygen is usually -2. Hydrogen is +1 with a non-metal and -1 with a metal. Oxygen is a non-metal, so my hydrogen in this case is going to be +1. Now let's double check this because it's always a good, this is 0 on this side, so this has to be a net 0. So I have a -2. I have 2 times +1. 2 times +1, so that's going to give me a +2 and a -2. Yes, that equals 0. Okay, so the question is this redox? And the answer is yes. You're going from a +1 to a 0 and a -2 to a 0. I will give you a hint. Anytime you see an element on one side of the equation and it's part of a molecule or compound on the other, it's immediately redox. Immediately. That's a quick way. If you're just having to say, is this redox or not? If you have an element on one side and a molecule or a compound on the other, it's redox, always. So the next part of the question is what is the oxidizing agent and what's the reducing agent? Well, first you have to find out what's being oxidized and reduced. The hydrogen is going from a +1 to a 0, so it's gaining an electron. Each hydrogen is gaining 1 electron, +1 and -1 to get 0. So it's being reduced. Therefore, it is the oxidizing agent. You want to make sure you don't give the wrong answer to that. If that's being reduced, that was my hydrogen. My oxygen, therefore, is being oxidized, and it is the reducing agent. And then if hydrogen is my oxidizing agent, this is the conjugate reducing agent, and this is my conjugate oxidizing agent. Okay? So even though your hydrogen and your oxygen are in one molecule, you will separate out and you will say the hydrogen, not an ion, this is not an ion, this is a molecule, is being reduced. It is the oxidizing agent. The oxygen is the reducing agent because it's being oxidized. Okay? So the first one, yes, that is a redox reaction. The second one is HCl. So we have hydrochloric acid plus sodium hydroxide. So we have an acid-base reaction here. Gives us sodium chloride. It's actually a neutralization because you have a non-water acid and base, and you end up with water. This is a titration, would be an example of a titration reaction. You have water as a product. Okay. Hydrogen is +1 with nonmetals and -1 with metals. Chlorine is a nonmetal. So my hydrogen is going to be +1. Same over here. My oxygen is a -2. My sodium is the 1A, and that's always +1. If you go back to the rules. I have a -2, +1 is a +2, so that's a net 0. I have a +1, so my chlorine is usually a -1, and this time it is. Net 0. Okay, chlorine is always +1. Oxygen is -2. Hydrogen is still with a nonmetal, so it's +1. I have 2 of them, so that's a +2 and a -2. That's a net 0. Chlorine is going to be a -1 to offset that +1 of the sodium. Is anything changing? My hydrogen is +1 here, both places. It's +1 here. My chlorine is a -1 here, and it's a -1 here. My sodium is +1, both sides, and my oxygen is -2. This is not a redox reaction. Nothing changed. The only thing you look at to determine if something is redox is, did the oxidation number change? No, they all stay the same. This is acid-base, this is neutralization, but it is not redox because there was no oxidation reduction going on. Okay, the third one, before aluminum, solid. Okay, right there you have an element. So if this turns into a molecule or a compound, same thing here, you automatically have redox. And it did. So right there, that tells you have redox. If you have element, even just one on one side, and is part of a complex on the other, you have redox. All right, these are both elements. That's the simplest one. It's just nothing but aluminum, nothing but oxygen. They are not ions. They each get 0. Oxygen, this is not a peroxide, so it's -2. We do not have a rule for aluminum. Now, I'm not looking at stoichiometry. You can do a redox oxidation numbers before you balance your equation. We're not looking at the coefficients. We are looking at the subscript. So I have 3 times -2, which is -6. This has to equal 0 because it's a net 0. It's neutral, net 0. So this has to be a +6 over here to balance out my -6 of my oxygen. But I have 2 of them. So each individual aluminum is +3. All right? +3 times 2 is +6, -6 is 0. So there are my oxidation numbers. Then the next question was, determine the oxidizing agent and the reducing agent. Not oxidize and reduce, oxidizing agents. So my aluminum went from a 0 to a +3. It lost electrons. It lost 3 electrons. It now has more protons than electrons. If it lost electrons, it's oxidized. Therefore, it is my reducing agent. Well, if that's oxidized, this has to be reduced. We'll check it. It goes from a 0 to a -2. It gained 2 electrons. Each individual oxygen did. And that gaining is electrons, is reduction. Therefore, it is my oxidizing agent. And then you would go over here. And this is a solid. This is not aqueous. This is not floating around. It is an ionic compound, but it's a solid. So this is my reducing agent. Then this is my conjugate oxidizing agent, my aluminum ion. And if the oxygen is my oxidizing agent, then the oxygen on my product side is the conjugate opposite of oxidation, reducing agent. Okay? So all you have to do is figure out one, and you can fill out everything else. Okay, the last one. This says magnesium solid. Well, right there, you should kind of perk up because you have an element. And if that element becomes part of a complex, you have redox. We have a solution. It says aqueous, which means this is actually dissolved. Why did I write so far down? Let me rewrite this a little higher. I don't know why I do that. So magnesium solid plus zinc nitrate aqueous, so it's in solution, gives us magnesium nitrate. So now the magnesium is in, do it again, plus zinc solid. So the magnesium becomes an ion and the zinc becomes an element. Definitely have redox. Let's go with the easiest ones. The magnesium solid is 0 and the zinc solid, that's a solid, is 0. Okay. This is dissolved, so actually it's zinc 2+ ion and nitrate ion. This is magnesium 2+ ion and nitrate ion. It's dissolved. It says aqueous. So this is what you really have in there, is you really have the soup of ions. So nitrate is a spectator. It's not going to be oxidized, reduced. It's picked up and it's moved. It's always going to be the same. That is a spectator. I'm just going to call nitrate with this, treating it as the ion of a -1. But my zinc is now a +2, and over here my magnesium is a +2. So we definitely have redox going on. My magnesium goes from 0 to +2. It's getting more of a positive charge. It has more protons than electrons, which means it lost electrons. If it lost electrons, it's being oxidized. And the question is, what kind of agent is it? If it's being oxidized, it's a reducing agent. Therefore, my zinc, and remember, not the nitrate, just the zinc, and you would call this zinc ion if you're asked the question. The zinc ion is getting reduced, and so therefore is the oxidizing agent. Our conjugate or pair, the magnesium is a reducing agent, and so the magnesium ion is going to be the conjugate or paired oxidizing agent, and my zinc is the opposite of this, the conjugate or paired reducing agent. Nitrate doesn't do anything. It's a spectator. It's just there, unchanged at the beginning, at the end. It's just, you can ignore it. If you're asked what is a spectator ion, it's nitrate. Okay, so that is how you calculate oxidation numbers. It's really bookkeeping. All you have to do is find out the status of one. You can fill everything out. So these were the 4 I just worked through. Number 1, 3, and 4 were redox reactions. Number 2 was not. And if you're only asked if it is or not, the fact that you have elements that become part of molecule or compound tells you right away, yes, it's redox. And then here you have each one worked out. Okay. So if you want to work through these on your own. All right, so the next lecture is going to be into predicting redox reactions, because we have a strength table that we're going to look at, and that is going to tell us if a particular reaction occurs or not. All right.